Hello, my name is Andrew Gary, and welcome to Seismic Soundoff, in-depth conversations in applied geophysics. In this episode, I speak with Henning Hoeber on a new tool for rock physics from his paper published in September's The Leading Edge. In this episode, Henning explains the theory of omitted variable bias and its connections to rock physics, why OVB hasn't appeared before in the geoscience literature, how this theory helps geophysicists understand biases in models, the real-world implications for improving a bias model, and how he will apply OVB to his future research. Visit seg.org/podcast to read Henning's article, as well as the rest of the links for September's The Leading Edge. This episode is brought to you by TGS. TGS offers a wide range of energy data and insights to meet the industry where it's at and where it's headed. TGS provides scientific data and intelligence to companies active in the energy sector. In addition to a global, extensive, and diverse energy data library, TGS offers specialized services such as advanced processing and analytics, alongside cloud-based data applications and solutions. Now for our conversation.
Hi, my name is Henning Hoeber. I'm a research principal with CGG. I'm in the research department, and I've spent a lot of time looking at seismic processing and imaging with particular emphasis on reservoir issues such as time-lapse and AVO.
Well, that is what we're going to be talking about today. You released a paper in September's The Leading Edge titled Model Misspecification and Bias in the Least Squares Algorithm, Implications for Linearized Isotropic AVO. Before we explore this method you outlined in your paper, why is model misspecification so common in linearized AVO?
I think there are a couple of reasons for that. And the first one probably is that the fundamental equations which describe what happens when a wave hits an interface and gets reflected and transmitted, the Knott-Zuppert equations, they're very complex. So you can stare at them as hard as you'd like. You'll probably get very little intuition out of them. So you simplify, and that means you linearize, and that allows us to then understand theoretically the effects that we're really interested in, such as disentangling, lithology, and fluid effects. But when you linearize, just as in a Taylor expansion, you have to decide when to stop. So do we just use one term, which would just be stacking, or two terms, or even three terms? And we often use just two terms, and it's not really laziness. It's to do with the information content in the pre-stack gathers, which is surprisingly low. So it's often not possible to obtain more than two reliable terms with the noisy data that we get. And in addition, there's actually quite a few different AVO linearizations, and that is because there are so many different elastic moduli that can describe the rock. So you can use a pair of elastic moduli in the density, and there's quite a lot of combinations of that, so you get just as many different AVO parameterizations. And when you then drop the higher order term, just as described, then you get different effects in terms of the linearization.
Well, there's a theory that plays an important role in the paper that many maybe not have heard of. So if you could explain to the audience, what is the theory of omitted variable bias, or we'll be referring it to as OVB?
Right, yes. OVB really just takes a closer look at least squares fitting, which is what we tend to do with our data. So it looks at what happens if we fit the data with a model, which is then missing some of the explanatory variables. So the easiest example is if we have a process which comes from some data which needs we just fit a straight line, a linear to it. This is similar to what we do in AVO two-term fitting. Then OVB analyzes the bias this places on the fit terms that we extract with the two terms, leaving out the higher order term, the quadratic term.
Why do you think OVB is not mentioned in the geophysical literature prior to this paper?
That is a good question, and I really don't have an answer to that. I don't want to sound too pretentious, but others before me have said that it's always a good idea to look across disciplines, and it's obvious that many good ideas and algorithms are found by exploring other fields. This is true of signal processing and imaging. It's perhaps more obvious these days when we have the whole field of AI and machine learning developing in front of our eyes. So I'm not sure why it hasn't been mentioned before.
Well, maybe a peek for the audience, how, I've definitely heard that a lot as well, as look across disciplines. So how did you operationalize that to come across this in the economic literature, and what made you see this connection to it in rock physics?
So to me, this has always been an area of interest, least squares fitting, and I was then recently asked by what we call the geo training in CGG to modernize a bit our AVO training, both internally and externally. And at that time, I then went and attended one of Pat Connolly's training courses on AVO and fluid lithology analysis. And that sparked my interest because I think I remember correctly that he said reliable AVO fits may only be achievable up to about 25 degrees of incidence angles. And that is significantly less than what most people use. So I think 35 degrees is quite a common maximum angle for AVO fits. Now, his reluctance to go beyond 25 doesn't just have to do with bias. I need to put in that caveat. It also has to do with signal to noise issues and other effects, stretch and attenuation and so on. But that comment, just as I was writing the training course, sparked my interest to go back and find an analytic way to analyze this problem with regards to theoretical error, the bias error that we make when we fit to only 25 degrees, or if we then go higher, how that changes the model parameters. And so I just started looking around the literature following the advice we just discussed, and clearly regression and multi-parameter regression is used a lot in economy, sociology, biology, and all sorts of other fields. And so it was more a random walk through the literature that took me there. And then as regards your questions for the rock physics, I was aware of some previous results, which are not too far off. So there's a couple of papers in particular by authors who at the time were with Hess. There's one in the leading edge and one in geophysics on AVO projections, which was a much read paper at the time in 2018. And in their leading edge paper, which they called Rock Physics Relationships Between Inverted Elastic Reflectivities, they preempt some of what I describe in my paper. But they didn't derive the results. So that also got me thinking, is this all the same thing? And it turns out it is. So the reason that rock physics relationships aren't always what you think they are is due to bias. So I definitely felt there was room to explain more why rock physics relations from least squares are not generally what they seem. And it so happens, I think, that OVB is quite ideal to see what's going on. More generally, perhaps, we do a lot of lower order fitting, not just in AVO, but also in rock physics. And so it seemed a good idea to sneak in what's probably a slightly more mathematical article into the leading edge. I didn't want to hide it in geophysics, although everybody advised me to put it into geophysics. And I think there's a final point, which is, we already mentioned, or I mentioned, machine learning. And of course, the issue of bias versus variance is at the heart of many of the algorithms in that field. And there too, one might ask the question, if the algorithms you should put the just in quotes, give us good data fits, or if they actually give us unbiased model parameters. So that's an area also of interest, which could be something to look at following the OVB analysis.
Well, this paper is a testament to continuing to learn yourself, and you're putting that into action there. How does the least squares algorithm work when it is functioning perfectly?
It is in fact BLUE, and BLUE stands for Best Linear Unbiased Estimator. So there's a theorem due to the famous Gauss and Markov, the Gauss-Markov theorem, and it says that the ordinary least squares estimator, which is essentially what I use in the paper, has the lowest error, or what statisticians call the sample variance, of all linear unbiased estimators. But, and this is a really, really big but, this is only true if the errors in the regression model are uncorrelated, have equal variance and zero mean. And of course that never holds with real data. You have all sorts of issues on real data that break the assumptions. And then when that, because of that, why are we still using least squares? Well, what we do before we apply least squares is we use various tricks, signal processing methods. So, for example, iterative reweighted least squares takes the data and reweights the data, and the weighting essentially moves everything back so that the assumptions of the ordinary least squares fitting are again true. And other methods, which are also popular, such as ridge regression, do something slightly different. And they will trade off a small amount of bias in the model parameters in order to decrease the variance, which is another trick you might play. So that's not really described in the paper, but it does mean that it's a good idea to think about what you do with your trickery, your signal processing algorithm, in terms of the bias, if you then want to use the model parameters in the rock physics analysis setting.
What happens to this algorithm when the model is misspecified?
Yes, so I think we just touched upon that a little bit. The assumption of the uncorrelated errors is then violated. So if you take the classic example of doing a straight line fit to something which has a quadratic variability, then the errors are no longer randomly distributed around your fit. So you can make a plot of the residuals. Like I do in the Jupyter notebook, and you will see that they're all correlated. And the reason for this is this problem of the bias can be understood intuitively as well. What we ask of the least squares algorithm is to minimize the sum of the least squares in order to best fit the noisy data. And for that, we give it a model. So it's really a data fitting method, and it's not a parameter prediction method. You might say that the model parameters fall out of the optimization, so to say, as a byproduct. And I have a couple of examples as well where I show that if you misspecify the model, you can still get very good data fits. The algorithm tries very hard to minimize those least squares errors, and it succeeds in doing that. But the outcome is that those parameters that you then have that fit the model, despite it being the wrong model, those parameters are then biased.
In what way does this theory of committed variable bias help the geophysicists understand the bias in the model better?
Right. So I think the first thing is that it's important to just know that this effect can happen, that it's likely if you oversimplify, even if you have good excuses for oversimplifying, such as the noise, that there is going to be bias in the model parameters. And I think you can then understand OVB in two ways, one which is the sort of the forward and one which is the inverse way. So first you can use the theory to forward model higher order fits using the what if idea, and that's really what I show in the paper. If I just use two fits, then you can ask the question, what if I had a curvature term in the data? What would that do to my model? How does that impact the intercept and the gradient? And the other way, which is really what the AVO projection paper by Ball et al. In Geophysics 2018 already showed, and I only really started understanding this after finishing the paper, is that you can start with a 3-term fit and then project down to a 2-term fit. So that again shows how the emitted variable, the curvature, then leaks into the 2-term fits, in this case, the intercept and the gradients. So that part of the theory is relevant to how we do AVO fitting. And in fact, one of the questions I get asked the most by practitioners of AVO fitting is, how do the AVO fit parameters change when fitting 3 terms instead of 2? And why do the intercept and gradient change at all? So we often start with a 2-term analysis, and then we might think, well, how would this change if we did 3 terms? And it's very annoying then when the intercept and the gradient change, even if you do the 3 terms over the same angle range. And in practice, OVB and the AVO projection analysis says we should probably think about this differently. We should always do a 3-term fit, because the 3-term fit can be used to project down precisely to the result of the 2-term fit.
Well, even going down a little bit more into real world implications, what are these, the real world implications of improving this biased model?
Yes, that's the $1 million question, and that's definitely a road I went down too while I was writing the paper and looking at this. It's unavoidable when you're thinking about bias. You always want to kind of not remove the bias. It's great to understand the uncertainty, but what about reducing the uncertainty, right? I think the ugly truth is that there is this thing that we discussed earlier, which is the information content of the pre-stacked data in this case, and that is fixed. Without adding more data or adding more information, that's not going to change. That's something that's inherent to the data that we've acquired. So in order to reduce bias or variance, you can trade the two against each other, which is what some of the algorithms do, or you need more data. So that really takes us into ideas which are more sort of part of Bayesian analysis, where you do want to recognize prior information. And also there's another technique out there called model-based fitting using principal component analysis, which was applied to AVO by Coase et al., which also leans on these ideas. But it needs more data or more information to reduce bias.
If a geoscientist is hearing about OVB for the first time, what other areas do you think this theory would be insightful?
Good question. So I think probably wherever we use simplified models, which is something that we do generally because the data that we've acquired at some stage isn't yet suitable to extract all the parameters that we know are really driving the wave propagation. So we simplify. And whenever we do that, we cut off certain terms in the modeling. So we should always ask then, well, what if that term is relevant and larger than I think what it is? How would that impact my result? And so this bias analysis allows you to do that. And what's also important in the context of the AVO setting is, of course, we're not interested in intercepts and gradients. What we want are quantities that describe the lithology in the fluid. So the next step in doing that is to propagate the bias through to those quantities that we're really interested in. And they might get amplified, or they might get reduced in that propagation. So we need to propagate not just the errors, the variance, but also the bias through to the quantities that we're interested in.
Is there something yourself you're looking forward to explore next with this theory?
I think it relates back to your question as to what other sources of bias are there. And of course, AVO, being the full analysis of all the data that we have, all the pre-stacked data, has a large amount of additional errors. I mentioned some at the start, the anisotropy, the angles, the attenuation, and so on. So then they're not necessarily all effects, I think, which fit into an omitted variable analysis, but they all fit into an uncertainty analysis. Which of these effects are really the dominant ones? So I'd like to set it into a larger context. It would be lovely, wouldn't it, to be able to forward model all of these errors and then to be able to rank them and say, well, in this kind of setting, you need to be aware of these errors the most. I suspect, though, that if I do that, our imaging colleagues will have made a lot more progress on yet more focused imaging using full waveform inversion and techniques like that, because there are a lot of effects in there.
Lastly, if you could just share one piece of advice you would offer someone looking to succeed in your field, what would it be?
Oh, I think I'm going to say something that a lot of other people say. Just remain curious and go and look at if you've got a particular problem in front of you, go and investigate how others would be looking at this. So precisely what helped me here was, even if it was just a random walk, but eventually finding how much of that regression analysis was being looked at quite differently in other fields.
Well, you are living that with this paper, Henning, and I appreciate you sharing your insights in the paper. And thank you for submitting it to the Leading Edge.
Thank you very much. It's been an absolute pleasure.
Thank you for listening to SEG's flagship podcast, Seismic Sound Off. SEG produces these episodes to benefit its members, the geophysics community, and inform the public on the value of the science. To show your support for the show, please share this episode with a friend, colleague, or manager that would enjoy hearing this show. Your recommendation is the single best action you can take on behalf of SEG's podcast. To receive the latest episodes first, follow Seismic Sound Off on Apple Podcasts, Spotify, or Google Podcasts. The SEG podcast team is Ted Bakamjian, Kathy Gamble, and Ali McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.